We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello dear students, today we will study about the 2 important mechanisms inside the bulk semiconductors, or we can say the group of semiconductors that takes place, that are emission and absorption. So basically, if we are considering these 2 important words, emission and absorption, suppose in a material when you are bombarding some amount of energy, then as per the properties of the material, some amount of energy will be stored by the material, that you can say that is absorbed by the material, and the remaining amount of energy will be dissipated, or you can say will be emitted. So the process of stored of amount of energy is called absorption, and the process of the dissipation of the energy or emission of energy, that is the important mechanism inside the bulk semiconductor. So as I told you earlier, that semiconductors absorb and emit photons of energy h mu by undergoing transition from valence band to conduction bands. As we all know that inside the semiconductor, the electron is traveling from the valence band to conduction band by remaining and occupying space for holes inside the valence band. But how does this electron travel from valence to conduction? By gaining the amount of energy that is equal to h mu. So the probability of absorption or emission will purely depend on the overlap and energy difference of the initial and final state and the density of these states. So how much amount of electrons or holes, any charge carrier you consider, how much amount will be absorbed or emitted, that means by gaining or losing some amount of energy, that depends on 2 parameters. Number 1 is the overlap, and number 2 the energy difference, that is the band gap. So in order to consider these 2 parameters, there are 2 different kinds of possibilities of transition in quantum structure. If you are considering any material, semiconductor, conductor, insulator or superconductor, so the transition of electrons will be of 2 possibilities. Number 1, the transitions between the valence and conduction band directly from valence to conduction, or the transitions between the quantum confined states within a given band, which is so called inter-subband transitions. This we will see clearly in this article. Number 1, the mechanism which we are going to consider here, that is absorption. In this figure, the bottom level which you are observing is nothing but your valence band, and the top level is your conduction band. The black dot on the valence band is traveling from valence band to conduction band, and you can see that the amount of energy h cut omega is absorbed, and this phenomenon is known as absorption mechanism. Here the graphical representation you are watching, that is EK diagram, energy wave vector diagram. In this mechanism of absorption, a photon is absorbed by the crystal and the energy of electromagnetic field is transferred to the crystal. So whenever electron is traveling from valence band to conduction band, remember the material will have the excess amount of energy. This process of photon absorption is also called stimulated absorption. This is very important. Here, the word stimulated absorption is utilized because, quite obviously, the process is initiated by the incoming radiation. See, here we are talking in terms of the traveling of electron from valence band to conduction band. Now, if you think, is it possible for electron to travel from valence to conduction band without any external energy? No. Thus, this process was purely initiated by the incoming radiation, or you can say photons, some of which eventually end up getting absorbed, and which has been clearly depicted from the figure that the photon of energy h cut omega is absorbed. Now, the second most important parameter is emission, and remember, here we are going to observe two different mechanisms. We have seen earlier in the Fermi's golden rule, which allowed electrons to make transition to states whose energy is lower than their initial energy by h cut omega. So, when electron is in the conduction band, which can make a transition to a valence band, but here when the electron is traveling in the reversal phenomenon, that means from higher energy level to the lower energy level, it clearly indicates the electron is losing the energy equal to the photon energy h cut omega. The energy lost by the electron goes to the electromagnetic wave, which initiated or stimulated the transition. So, the loss amount of energy is particularly utilized by the electromagnetic wave, which we are going to analyze in detail. Here in this figure, again EK diagram, but just the reversal process. You can see now the black dot of electron traveling from the conduction band to valence band. Quantum mechanically, that means at very micro level, we say that the electron in the conduction band emits a photon. Now see, the emission of photon on the right hand side, h cut omega, and makes a transition to the valence band. This process is called a stimulated emission. So, when electron is losing some amount of energy and traveling from conduction to valence band, that process is known as emission, because here the energy is emitted. In addition to the stimulated emission process, remember this is very important, an electron in a higher energy level can spontaneously, remember this is very important, spontaneously, that is in the absence of external electromagnetic field. Here when we are considering the traveling of electron either from valence to conduction band or from conduction to valence band, there is a need of external electric or electromagnetic field. Remember this is very important, but here we are talking in terms of the spontaneous mechanism. That means there is no external electromagnetic field is applied. In this case, if electron is emitting a photon and still it is transiting to a lower energy level, this process is called spontaneous emission. So here in the emission mechanism, we have to consider two different parameters, stimulated emission and spontaneous emission. Here again the figure below depicts the spontaneous emission process for an electron initially in the conduction band. Again it is a very well known EK, that means energy wave vector diagram. Electron is traveling from conduction to valence band and it is emitting the energy equal to the photon energy h cut omega. You can either write down h cut omega, or you can also write it as h mu. In order to determine the emission and absorption rate of the bulk semiconductors, here till now we have considered the absorption and emission mechanisms takes place inside the semiconductor. Now suppose I have a semiconductor material like silicon or germanium, but how can I identify that this particular material is emitting electrons at this particular rate, or it is absorbing the electron at this particular rate? So in order to determine the emission and absorption rates, it is very much necessary to consider their band structures. And in case of a spontaneous emission in a semiconductor, the energy states, that is E2, that is a higher energy level, is occupied by electron, and we have to consider the lower energy level E1, which is unoccupied, or you can say it is occupied with the holes. And hence the occupation probabilities for electrons which were earlier in the valence band and which further travel to the conduction bands are described by very well known Fermi-Dirac distribution function. So the occupation probabilities for higher energy level is given by equation number 1, FCE2. The FC stands for conduction band, E2 is the energy of the higher state, that is conduction band, is equal to 1 plus exponential E2 minus EFC divided by kBT inverse. So kB is the Boltzmann constant, T is the absolute temperature in Kelvin. Again, FVE1 is equal to 1 plus exponential E1 minus EFV upon kBT inverse. FV is the occupation probability for electrons in valence band. Here in equation 1 and 2, the right hand side term have EFC and EFV. These are nothing but the Fermi energy levels. Expressions give the probabilities that the states in the conduction bands above or below the Fermi levels will be occupied with electrons. As the temperature increases above absolute zero, the probability of occupying energy levels above and below the Fermi energy becomes more gradual, and which can be easily seen from the Fermi energy function versus energy band diagram. As you can see, at absolute zero temperature and the temperature greater than absolute zero. So what is the total spontaneous emission rate? That is RSPV is equal to integration EC to infinite from conduction band to uppermost or atmost higher energy level A E2 E1, which is a function of the energy, FC E2 we have seen earlier, 1 minus FV E1 Z E1 E2 into DE2. Here A and Z are nothing but the energy function, or you can say absorption function. Moreover, the total absorption rate, remember here we have to identify three equations, one for stimulated absorption rate, one for stimulated emission, and the last one for spontaneous emission. So the total absorption rate, that is R absorption V is equal to integration EC to infinite B E to E1. See in equation 3 and 4 how you have to identify the equation. The only change first of all in the energy function. After that, absorption takes place in the valence band, emission takes place in the conduction band. So instead of FCE2 we have utilized FVE1 into 1 minus FCE2 ZE1E2 as it is, rho pH, that is the density of photon, mu DE2. Similarly, equation 4 and 5 are almost identical. Total stimulated emission rate R simulated V is equal to integration EC to infinite, which is almost similar, B E2 E1 FC E2 1 minus FV E1 Z of E1 E2 rho PH, that is photon, V DE2. So this was the Fermi-Dirac probability distribution function with which we can easily identify the total spontaneous, total absorption and total emission. Now, why these absorption and emission rates are important? Because when these semiconductor materials are being actually utilized in various application purposes, so as per the criteria of their absorption and emission rate, one can identify their applicability approach or their actual mechanism of action for their purpose area. And hence, with this absorption and emission mechanisms inside the semiconductor, that article is over. Thank you for visiting this lecture.